Einen wunderschönen guten Abend, meine sehr geehrten Damen und Herren, und herzlich willkommen zur Eröffnung der Ausstellung BarabásiLab Hidden Patterns Network Thinking, also verborgene Muster, vernetztes Denken. Sehr gerne hätten wir Sie hier im Haus in Empfang genommen, sehr gerne hätten wir die Ausstellung analog eröffnet. Aufgrund der Pandemie ist das immer noch nicht möglich. Nichtsdestotrotz wollen wir es uns nicht nehmen lassen, Sie heute bereits in diese Ausstellung einzuführen, die eine sehr spannende, eine sehr aktuelle Ausstellung ist, und möchten Sie zunächst einmal auf einen kleinen Rundgang mit dem Künstler Albert-László Barabási schicken und danach noch in ein sehr spannendes und aufschlussreiches Gespräch entführen.
Good evening and a very warm welcome to all of you who are joining us tonight for the digital opening of the exhibition BarabásiLab Hidden Patterns Network Thinking. Unfortunately, due to the restrictions of the COVID-19 pandemic, it is not yet possible to open the exhibition physically, so we cannot welcome you here at ZKM in person. Nonetheless, we are having a wonderful, very exciting evening ahead of us to celebrate this new exhibition. After a digital guided tour with Albert-László Barabási himself, we are looking forward to a digital panel discussion with Peter Weibel, Albert-László Barabási, Isabel Mireles and Alice Krischenko on the topic of network thinking.
Ja, die Daten unserer Welt wachsen heute exponentiell und auch das Wissen der Welt verdoppelt sich alle 2 Jahre. Um diese riesigen Datenmengen zu bewältigen, braucht es einer neuen Wissenschaft, braucht es neuer Werkzeuge, und die Datenvisualisierung ist ein solches Werkzeug, dessen wir uns nun bedienen können und das es uns ermöglicht, Daten durch Netzwerke wahrzunehmen und zu verstehen, die durch die Verknüpfung von Knoten und Links Gestalt annehmen und einzigartige Formen erzeugen, die bisher unsichtbare Verbindungen und Muster beleuchten. Das innovative und interdisziplinäre Feld der Netzwerkwissenschaft ermöglicht tatsächlich die Analyse verschiedener kultureller, biologischer und sozialer Phänomene und macht sie durch visuelle und grafische Darstellung nicht nur sichtbar, sondern auch verständlich. Genau in diesem Bereich setzt die Arbeit des BarabásiLabs an.
Data in our contemporary world grows exponentially. Also, the world knowledge doubles every 2 years. To cope with the huge amount of data, a new science and new tools are needed. Data visualization is such a tool that allows us to perceive and understand data through networks, which take shape by interconnecting nodes and links, producing unique forms that illuminate previously hidden and invisible patterns and connections. The innovative and interdisciplinary field of network science enables the analysis of various cultural, biological, and social phenomena and renders them not only visible, but also comprehensible through visual and graphic representation. This range is exactly where the work of the BarabásiLab begins.
Die Ausstellung BarabásiLab Hidden Patterns stellt die Arbeit des Physikers und Netzwerkswissenschaftlers Albert-László Barabási und seines Forschungslabors, seines Forschungsteams dar, die an der Northeastern University in Boston angesiedelt ist. Und die in Kooperation mit dem Ludwig-Museum Budapest realisierte Ausstellung bietet tatsächlich erstmals in Deutschland einen umfassenden Überblick über die vom BarabásiLab, also einem Kollektiv aus Wissenschaftlern und Designern, realisierten Projekte, und sie spiegelt die Entwicklung der Netzwerkvisualisierung der letzten 25 Jahre wider. Dabei konnten sogar einige der jüngst veröffentlichten Projekte berücksichtigt werden, wie zum Beispiel das Cyber Art Network Projekt, das sich mit dem aktuellen Phänomen der NFTs, der sogenannten Non-Fungible Tokens, beschäftigt, aber auch ein Projekt, das die Covid-Pandemie näher untersuchte, oder das Genome-Projekt, das wir jetzt schon seit einigen Jahren kennen. Um Ihnen einen besseren Eindruck von der Ausstellung zu vermitteln, laden wir Sie jetzt ganz herzlich ein auf einen Rundgang mit dem Künstler und Wissenschaftler Albert-László Barabási. Viel Spaß!
The exhibition BarabásiLab Hidden Patterns introduces the work of the network scientist and physicist Albert-László Barabási and his research laboratory based at the Northeastern University in Boston. Realized in cooperation with the Ludwig Museum in Budapest, This exhibition offers for the first time in Germany a comprehensive overview of the projects realized by BarabásiLab, a collective of designers and scientists, and reflects the development of network visualization over the past 25 years. It was even possible to include some of the most recent published projects by BarabásiLab, such as the Cyber Art Network, which addresses the very topical phenomenon of NFTs, or Drugging COVID, or the Human Genome Project. To give you all a better understanding of what you will expect in this exhibition, we are very happy to pass on now the word to Albert-László Barabási himself, who will give us a digital guided tour throughout the exhibition spaces.
It's a real pleasure to welcome you to the BarabásiLab exhibit at ZKM that is opening today. And what I would like to start this guided tour with is to understand that I am Albert-László Barabási, but this is not my exhibit. There is a reason why it says BarabásiLab on the wall, because this exhibit really captures the last 25 years of visualizations that were produced by a collective of scientists as well as designers with the purpose of really understanding complexity and understanding networks. I'm a network scientist, meaning that I study various complex systems, the cell, the universe, the social systems, economic systems, and try to understand the connections between the pieces in those systems. And part of our scientific practice, we also developed a whole line of research and thinking about how do we visualize these networks. And we did so not for the primary purpose initially to be in the museum with them, but mainly to understand these systems, to really understand complexity, to be able to see that. And what you see here at this exhibit is a selection from those visualizations that we have done. I like to start the exhibit at this particular image, which in a way dates my interest in network science as well as our interest in network visualization. I know exactly when, for the first time, the concept of network occurred to me. I was working at IBM right after my PhD, and for Christmas I took home a book. The book focused on computer science, and within that book I found a little article focusing on computer networks and networks as a mathematical object. At that time, I was living in New York City and made me realize how many networks make the city work. The communication network, at that time, the internet was just emerging, phone lines and so on. And I realized there's so little understanding of these complex networks around us. So I decided at that moment, during that Christmas break, that I will focus on networks to understand complex networks. And what is interesting is that the first product of this thinking was not a research paper. It took several years for me to publish a paper, but rather this particular visualization. This image is also very well dated because we have the original print from the IBM computer that dates it as 1995, January 17, which implies that 3 weeks after I started thinking about networks, my first step was to visualize. What did I visualize? In this case, I visualized the network of water as it enters the ground that is common, for example, in oil exploration. And in particular, I visualized the mathematical model that describes that particular process. And what is interesting from a visual perspective, that this particular image kind of aesthetic look is very deeply rooted in my training as a physicist. I show a network as a lattice with only straight lines corresponding to the links, and the nodes don't yet appear. And we will see that with time, that particular representation drastically changes. But nevertheless, this is where our journey begins. As I mentioned, the first visual language was that of a square lattice in 1995. But in 2000, 5 years later, by which time we started to publish on networks, the whole visual language changes. Now you see explicitly the nodes, and the nodes are colored. That is, the node color carries information, and they are connected so far with straight lines. And the 2000 image is still depicting a model network, in this particular case, the so-called random network. But soon after, the year after, in 2001, we start showing real networks. And that change becomes a hallmark of the lab's visualization, because what you see in the 2001 image is already the protein-protein interactions based on experimental data and how the proteins are connected within our cells. In 2004, we are faced with another challenge. We need to have information about the links themselves, so we start coloring the links to show the fluxes that flow, in this case in the metabolic network. And in 2007 is the first time that we start encoding information into the node size as well. And this came in the context of human disease network. 2011, we encounter very dense networks where the straight lines don't actually do it any longer because it's too confusing. So we start developing algorithms to curve the links to avoid the dense areas. And 2018 is another major change in the way we represent networks, because for the first time we are able to step out of 2 dimensions and enter the 3rd dimension. That is to really start printing 3D data sculptures. A year later, in 2019, the technology emerges to do that in color as well. That is to encode information into data sculpture by coloring the nodes. And in 2020, we encounter so complex networks that it's impossible to really even print it, and those are shown in virtual reality. About 3 years ago, I got a very unexpected request from the journal Nature. As many of you know, Nature is one of the most influential scientific magazine out there, and the editors were getting ready to celebrate the 150th anniversary of the journal. And they came to me and asked me if I could help them design the cover for the anniversary issue. This was an unexpected request in a sense that it was the first commission we ever got to visualize something for the sake of visualization. And we approached it from a data perspective. We started by first mapping out about the 80,000 papers that Nature published in the last 150 years. And then we were looking for hidden connections between them. That is, in this image, what you see behind me is all the papers that Nature has published shown as individual nodes. The colors correspond to what disciplines we have: physics, biology, social sciences, chemistry, ecology, and so on. But the links are not links that would be obvious if you read the paper. The papers were connected if they are connected in the scientific community's mind, if in the mind of the researchers there is a connection between them. And how do we extract that hidden knowledge? We did so by finding how often 2 papers were cited together in the scientific literature. Because the more often 2 papers are cited together, the more related they are in the minds of the community. Hence, on the map, you see regions of similar color, like yellow color, blue regions, and so on. And that's because physics papers tend to be cited together, and biology papers tend to be cited together. But you see also papers that have different color and they're connected, because those are what we call interdisciplinary or cross-disciplinary papers that multiple communities find it to be interesting. In many ways, this image shows the extreme complexity and heterogeneity of science itself, the existence of the multiple fields. But it also shows that they are not disparate disciplines. There is a conversation between the disciplines, and those are captured by these hidden connections that we have between the different papers and different disciplines. The project resulted in the Nature cover that is shown here next to me. But at the end, we had so many interesting visualizations that the 1-page request to design a 1-page cover turned into a 5-page cover that is a fold-out right now, showing first the map itself, and in the back of the fold-out, we also showed the impact of the individual research papers, where they were inspired for. They're shown as a caret, and also what kind of research did they inspire. What is interesting about our visualization journey is that a few images have been published, either as the cover of a journal or they are inside the research paper. but they are accompanied by many sketches, as I would call them, or many trials. And I also want to emphasize that for us, visualization is not only for the final product, but also to understand the systems that we're studying. What you see next to me on the left and the right are those sketches that preceded the final product. And what you may recognize is a kind of a black and white version of the final nature cover, where we're trying to work on different type of layouts. And while these images all look alike, or at least 3 of them look alike, if you look closely, you will realize that there are very fine differences between them. And those fine differences are really looked at when we're trying to decide what should be the final layout. The one on the other side is also one of my absolute favorites. It's a protagonist to the carrot image that ended up in the back of the nature cover. And we ended up not using this particular representation, but I thought visually this was really stunning. So I really wanted to have them in the museum exhibit. And it's also important because we use these images to show how much in the lab in the last 25 years have worked proverbially for our drawer, that we created hundreds and I would say thousands of images that we knew that we will not be able to show. Nevertheless, they were a very integral part of the journey. What you see here is the universe as a network, galaxies connected to each other through the gravitational forces that hold them together. And this is a beautiful representation of the collaboration the designers and the scientists have in my lab. These images were generated by Kim Albert, who is a German-born designer who came and worked for 2 years in my lab, and now he's back to Berlin, where he continues to work in design. And when he joined my lab, he was embedded in a group of physicists and astronomers, because at that time we were interested in trying to figure out how do we think of the universe as a network. And the result of that journey was a research paper in which Kim himself was a co-author as the designer, because it was so much based on the visualizations. But obviously there were lots of other scientific results as well. In many ways, the images that were created from that, the video that you see in this exhibit, as well as the prints, offer a stunning representation of the cosmic web. Because we tend to think that the stars and the galaxies are lonely objects. In reality, they are not. They are connected by gravitational forces, and the evolution of the universe is determined by this cosmic web. And we wanted to bring this cosmic web back to us so that we can feel it, we can understand it. What you see on this map is what we call the flavor network. And when we generated that, we were trying to answer a very simple question about food. What are the ingredients that taste well together? That is, what are the ingredients that we should really mix in our food? And we were inspired by a hypothesis from molecular cuisine that said that 2 ingredients taste well together if they share the same flavor chemical. It's a little bit like dressing up and matching certain colors so that we have some consistency there. So therefore, we created a network where the notes are the different ingredients in our food, and they are connected only if they share not one but several flavor chemicals. That is, they have a similar flavor components. For example, you see there's a connection between cocoa and coffee because they share multiple chemicals that defines their taste. Now, the question is, what did this map tell us about what tastes well together? And in a way, it said that the molecular cuisine hypothesis is right and wrong depending on where you look. Turns out that the Western cuisine really prefers to combine ingredients that have many chemicals together, but the Eastern cuisine is combining complementary ingredients, those that don't share flavor chemicals. This map was also the one where we first had to curve the links because it was too dense for us to be able to see how the different pieces are connected to each other. And particularly if you look in this region, you see that there is a cacophony of links that is very difficult to disentangle. So I want you to kind of remember that because we have another solution to this problem. Indeed, because mathematically we know that in 2 dimensions we can never represent a network without the links crossing each other. but we can do so in 3 dimensions. Let's see how do we do that. The network you see here is identical with the flavor network we just saw earlier. The major difference is that that was in 2 dimensions and this was in 3 dimensions. Now, why 3 dimensions? Well, on one end, before I became a scientist, I was studying to become a sculptor. And thanks to that experience, I was always frustrated that network visualization is stuck in 2 dimensions. We produce images for the screen, for a piece of paper, and not really showing them in 3D. On the other hand, there's a mathematical theorem to tell us that any network can be laid out in 3 dimensions without the links having to cross each other, versus in 2 dimensions where they must cross. So therefore, since 2007, I've been trying to find a technology through which we can bring the networks out from the computer screen. We succeeded around 2017 and 2018 when 3D printing emerged to the level that we could actually start systematically print networks. Now, looking at the 3D version of the flavor network, you realize how much more content has emerged that you could not do in 2 dimensions. But the most important question is that how do we lay it out? How do we decide where the nodes and the links are? And in order to do so, we have to build algorithms, or in other terms, we need to formulate the aesthetic problem of a good network layout in terms of the mathematics of the problem that the computer can understand. And hence, the principles that we use are summarized in this equation. So this is the equation that the computer sees, and the way it does it is shown actually in this video. It solves this equation as it's searching for the layout that really captures the best the structure of the underlying network. And you can see it unfolding and finding the final structure will end up actually in this particular structure. What is being encoded in that equation? What we encode is that we want the nodes who are densely connected to each other to be next to each other. That is, the communities to correspond to nodes that are close to each other, and those who are not connected to each other could be far away from each other. So when you look at this network, it really reveals the underlying structure of the system. And now we also have a mathematical methodology as well as a technology by which we can take arbitrary networks and lay them out in 3 dimensions and give a very different experience and different way of interacting with the network itself. One of the problems with the 3-dimensional sculpture is the information about the nodes and links is lost now because we cannot color the nodes easily. That information is given back to us with augmented reality. So if you come to the exhibition space and you get this iPad, then the iPad now will reveal the identity of the nodes. So for example, it will tell you that that big central node over there corresponds to cocoa, and next to it there's rose and so on, and it will tell you that these are mostly cheeses, and these correspond to mostly fish, different type of fish, and down here we have the fruits. So augmented reality gives a possibility for us to regain the content that is lost by simply looking at the structure of the network, but the structure itself now is much more revealing than what we could get in 2 dimensions. The possibility to bring back the content is thanks to MOME, the university in Budapest, and several creators who worked with them, who created this interactive feature that we can regain the content from any 3D sculpture and kind of reveal again what are the nodes and what are the links. These are researchers and designers from the Moholy-Nagy University in Budapest who have worked tirelessly to make this possible for us. The 3D printed networks are also interesting us for another reason, because they're examples of physical networks. And why physical networks are networks where the nodes and the links have physical existence. And we're interested in them because they mimic real systems in which physical networks emerge, like the brain. What you see on my left and on the right-hand side is a neural map of the mouse brain, of the same mouse brain, as a matter of fact, one as a light box and the other case as a video. And what it illustrates is the dense environments in which the neurons exist. So the difference, say, between the Nature 150 work and this one is that in many networks, the links are virtual. They just represent some association between the links. In these cases, the links themselves, the neuron, take up space and they push against each other. And that physicality determines the structure of the network. So one of the big research projects that we have in the lab is to understand physical networks. And this is all motivated by the brain as a network. We hope this understanding will help us understand how the brain has emerged and how it functions. The 3D networks that we saw earlier corresponds to only one limit of a physical network, or one phase, as we like to say. And in a counterintuitive fashion, this fat gurka, as we call it, is really a physical network, but corresponds to the other limit of it. The way we should think about it is that the statue that we saw earlier is like water, and this is ice. And here what we're showing, what happens if a network becomes more and more crowded. As the links are increasing in thickness, there is less space for them to find their location, and they must push against each other. And then you end up in this very stressed state that we call it the gorge, or the gurkas, the Latin word for gorge, because really there's no space for the links to find their destination. Why is this state important? Because this is the state that really describes our brain. We tend to think of the brain as being a network where everything is connected to what they should connect to. But in reality, in the brain, things are only connected to what they can, because they're in a very dense environment, the neurons themselves. And mathematically, that dense environment is described by this gurka object. This is a static image of that. And what you see on the video is how do these gurkas emerge? How you go from a very thin network where there's lots of space between the nodes and the links to the very stressed and dense network state. In physical networks, the links don't have the luxury to go straight to their destination. They must curve to avoid each other. So for several years, we were working in the lab how to describe this curving process. How do we characterize and distinguish a curving link from a straight one? And hence we introduced the concept of the link temperature, the network temperature. That just like in the air, if the air is hot, the molecules move very fast. And as it cools down, they move slower and slower. We ended up assigning high temperature to the links that need to curve very much and low that go straight. But we didn't have a good way of representing that. And in 2019, in the summer, I was in Vienna at the MUMOC to see an exhibit about op art. And I saw the many square lattices the artists were using. And that inspired me to really think of the heat as a way of represented by a square lattice. So what we did in this particular image is that we changed the temperature of the links by making it very hot in the middle, hence the links are very curvy, and decreasing it towards the edge of the lattice. And that generated this amazing final representation that is, by the way, on the cover of the catalog of this exhibition. How does an idea become an artwork in a museum? And as I mentioned, it was in MUMOC when I got inspired by the lattices, and then I went back to Budapest and I said, how could we show this hot network? And I ended up drawing this. I draw lines that the temperature is increasing, then I draw a square lattice where the center is increasing and becomes hotter and hotter. And then I wrote an email that you see over there together with the drawings, and I sent it to Yan-Chin Liu, my student in Boston who was working on the hot lattices. And I asked him, could you implement algorithmically this increasing temperature towards the center of the network and show me what you got? And when I got about a week later the image, I was totally impressed. That is the image that we saw earlier, which is now on the cover of the catalog. So when the COVID came, we were wondering how could we create a work that really represents this moment. So we ended up getting data from New York City of mobile phone information, how many people are in the city, and we used the long analog where the map of the city was expanding the more people can be found at that given hour within the town. And we used the long analog because my lab has been studying a lot lung disease. And you see that as during the day, they expand and then it starts shrinking. But it should not escape anyone that we're talking about March 14 over here. So this is the time when COVID was already present in New York, but people were not yet used to it. But then the week after, you actually start seeing that fewer and fewer people are coming to the city, even though they could. And hence the lung is not expanding as far. It is not such an expanded breathing. And then of course comes March 21st, when effectively the city is shut down and the lungs are collapsing. What is amazing for me is not the fact that when the city shut down, the whole lung, the city collapsed, but the emergence of a new normal. So New York City in the coming weeks continues to breathe. During the day, people come in, workers come in to do the essential services, and then during the evening they leave. But it does so as a sick lung because the amplitude of the motion is much more reduced. I call this work my 21st century because I really do believe that March 21st, when New York City as a lung collapse, really marks the beginning of the 21st century. In the same way that it's hard to remember what happened in the 20th century before the First World War, I believe that generations later we will look back at the COVID moment of March 2020 as the beginning of the 21st century. What you see here is what we call the human disease network. And the origin of this map goes back to me returning to Boston in 2005 and joining the Dana-Farber Cancer Institute. And 2005 was a few years after the Human Genome Project. All my colleagues at Harvard Medical School were discovering new disease and gene associations, that they were discovering almost on a weekly basis genes that cause certain diseases. And what I became curious is that how do we conceptualize all of these independent discoveries? And hence we built this map where each node corresponds to a disease, and the size of the node corresponds to how many genes were known to be associated with that. So you see deafness as the biggest node here because about 33 different genes were associated with that. The colors of the node correspond to different classes of diseases. For example, here you have mostly cancers in blue, and two diseases are connected to each other if the same gene is responsible for both of them. So for example, when you look at diabetes and obesity, these are very related diseases and they have multiple genes that kind of link them together. In some way, this image was the lab's most reproduced image historically, because for the first time around, both researchers as well as those interested in medicine to really see the full landscape of diseases and the connectedness. And it showed us that diseases for which you see not only different doctors, but you go to different hospitals at the genetic level are connected to each other. Originally, it was published as an image in a figure in the National Academy of Sciences, but the National Academy also carried a poster with the paper that became very popular. And then the New York Times carried a full-page version of this image. But it was also this map that really started our conversation with the art space, because Hans-Ulrich Orbist from the Serpentine Gallery has found this image and the flavor network and exhibited it at the Serpentine and eventually put it in the catalog. And it was the first time really that one of our maps really emerged in the art space. What you see here is a brand new project. In 2021, we were asked by Nature to again work together, and this time to create a cover for the 20th anniversary of the Human Genome Project, the project that inspired the Human Disease Network. So I was delighted to work with them again because I felt like we came full circle. And what you see here in this room is an ability to see how you can represent the same data in many, many different ways. What ended up on the cover is this representation, an iceberg analogy, where what you see as circles, and you see it particularly well here, each circle corresponds to a chromosome in the human genome, and the circles and the smaller circles inside the big circle correspond to the individual gene on that particular chromosome. But there's another layer of information encoded onto that, which is how much research has focused on that particular gene. So if particularly here you see the p53 gene, this is the so-called cancer gene, an extraordinary number of papers have focused on that, and the size of the circle corresponds to how much research has really been focused on that particular gene only. You can see from this image that a few genes got exceptional amount of attention, but most of them have been really ignored by the research community. This is the representation of the same idea, except that the iceberg now encodes two different types of information. What you see above the waterline is how much was known about the gene before the Human Genome Project. And what you see under the waterline is the new knowledge that the Human Genome Project brought to us, that how much research has focused on those genes after they have been mapped out. In a way, illustrating how much was under the water that at that time was unknown to us. This image encodes exactly the same information as the iceberg one that we just saw a second ago. But now the impact of each gene corresponds to different buildings, so we chose a city landscape to represent it. And the height of the building corresponds to how much work has been done after the Human Genome Project. And the shadow corresponds to how much was known before. So if you look carefully, you would realize that not all buildings have a shadow proportional to their height, because the amount of interest often before and after the Human Genome Project was different. And on the left-hand side, you see again the same data being represented. But now we used, instead of a city or instead of an iceberg analogy, one of a cell's nucleus, where we crumpled the genome, those circles that we saw earlier, inside a sphere, kind of mimicking the fact that the genome itself is deeply crumpled inside the nucleus. And to encode information about how much interest is about the particular genes, the thickness of the line, the thickness of the genome itself is varying to encode the amount of research focused on that particular region of the genome. The colors correspond to different chromosomes. And in a way, what I find totally amazing about these three images is that how many different analogies and how many different language and vocabulary you can develop to show the same data. And what is common between them is the accuracy of the data. That is, we have a fidelity to original data, but we have a very, very different visual look that we generated for them. So when COVID came, my lab got deeply engaged on trying to find drugs to cure COVID patients. And the goal was really not as much to design a new drug, because a new drug takes often a decade or two to really be introduced to patients, and there was no time for that, but rather to find out whether any of the 6,000 already existing drugs on the market could really help cure patients with COVID-19. And for that, we developed a whole set of network medicine-based tools that looked at every single drug and said, could it potentially be effective against COVID-19 by seeing what are the targets of the drug. And through that process, we predicted a series of drugs that could be effective, and then we experimentally tested that. This project over here is generated to show that extreme search process that we have to go through to identify the few drugs that may be effective. If you come and interact with it, this is an interactive installation, you will have the option to really select a particular drug on the screen. And once you do that, then the next image, once you have kind of selected, and here I'm going to select newly another drug over there by clicking on it. And once you achieve that, then on the second screen, we will actually get to see where are the targets in the large network of the human protein interactions of that particular drug. And then on the other screens, we show the evidence whether this should or should not work for COVID-19. And in particular, on the bottom screen, the red screen, what we see is that not only we theoretically predicted what should work using the network, but also our colleagues at Boston University ended up experimentally testing each of them. And in that particular image, When you see a blue region, it means that there is a cell there. But if it's surrounded by a red region, it means that inside the cell there are COVID viruses. So that cell has been infected. And those where you are lacking the red region, it means that on that region, that particular drug did manage to kill many of the viruses. In this particular case, the molecule we look at it was somewhat effective to kill the viruses because there are big regions of the plate where the virus is missing. We ended up representing this whole research project, that desperate search project for a drug, in these particular videos, but they also, the successful finds are shown as glass boxes over there. We have about 10 boxes, each of them corresponding to a different drug and the network within the cell that allowed to correctly predict the effectiveness of that particular drug. The way I think about the data and the visualizations is to kind of create multiple sketches to represent the ideas. And this wall shows a subset of the many sketches that I created in the last few years that I use for multiple purposes. I use to record inspirations from artists that I see, or even from nature or from science. I also use it to offer feedback to my lab and my colleagues as they process certain images. I use sketches to design certain new situations and new artworks. And I use them also to capture ideas about the journey in the art space. And I was delighted to see that the curators decided to put a selection of these sketches over here. If you look carefully among these images, you will recognize the predecessors of many of the projects that we see, or you will see process images as they evolved, arriving to the shape that are shown in this particular exhibition. In 2018, we decided to take the tool set of network science to really reflect on art and the organization of art. Why would we do that? Because I believe that really art and the value particularly in art is generated through a network. That is, whether a certain object is valuable or not, it depends on who touched that object. Where do you see that? What museum? Is the prestigious museum or not so prestigious gallery? What did the artist do before and what did he do after? But the question is that how does this value really emerge? And in order to understand that, we ended up mapping out the history, the exhibition history of about 500,000 artists. And from that, we generated a network of institutions. And the network that you see here is the result of that project where each node corresponds to an institution. The size of the node corresponds to the prestige of the institution. So here you see MoMA, Guggenheim Museum, Pace Gallery, and many of the top European institutions, including ZKM. And two institutions are connected if they tend to exhibit the same artist. Why is that link meaningful? Because if two institutions exhibit the same artist, like the BarabásiLab has been exhibited at the Ludwig Museum and now at ZKM, it shows that the two institutions have a different conception of what contemporary art really means and what is value in art. This network was very unexpected for us because on one end, of course, showed that the high-profile institutions all form one cluster, which means that they tend to exhibit the same artist. They're fighting for the same artist. But it also showed the existence of multiple communities of institutions, often geographically organized. Here you see Eastern European institutions, and here you see Oceania and Australia, that form separate islands on the art network, meaning that you can be an artist who goes from one institution to the other one, and you have a lifetime full of exhibition opportunities to be part of the art world, but you have no path in this journey from here to the high-profile institutions in the center of the art world. We were able to use this data to predict even the future career of the artist. If you give me the first five exhibitions of a particular artist, depending on where he or she starts from, we can tell you where they're going to get 20 years later. Why can we do that? We can do that because the art really works through a network effects. And these are very embedded in the way value is created in the art world, and this particular map captures that. What you see here is a work that is really a few weeks old, and I'm totally amazed that could be part of this exhibition. And what it represents is one of the hottest trends in the art space, which is NFTs, or non-fungible tokens. In March, the whole idea of NFTs in art have really exploded thanks to some very high-profile sales, which inspired us to start looking at the network effects of how NFTs have emerged. What is amazing about NFTs and generally crypto art recorded through these NFTs is that it's a totally open market. That we know who the artists are, and we know who is the first buyer. That means we know the primary market. We know how much they sold for, and we know how much they paid for those who purchased from the primary market, that the secondary market can be mapped out as well. And in this case, we created a map of one of the most highest profile NFT markets, so-called super rare. Each node here corresponds to an artwork that's sold on super rare in the last 3 years. That's the total length of the market itself. And 2 nodes are connected if during their lifetime they were owned by the same owner, that is, where the same collector has kind of had them. And when we mapped this out, we were puzzled by the existence of these very clear communities. And first we thought that these artworks that are all kind of seem to be owned by the same group of people, they're so connected, maybe they are connected because they are by the same artist. And that didn't really explain the effect. And then we realized maybe we should actually color this map based on who owns the work right now, based on the current collectors. And that suddenly made lots of order. So colors correspond to who is the current owner of the work. And it shows the presence of a couple of really massive collectors that really own this work. In many ways, this is no different from how a new ism emerges in the art world. We find that 87% of the artists, of the collectors buy the work, but they don't sell it again. So they hold on to it like many real world collectors do. And we also find that there are these large collectors, which, for example, are well known to exist, for example, even among impressionist artists, who a few early collectors ended up purchasing many of their works and then reselling it to the larger community. In many ways, the art network that we saw earlier describes the traditional art market, where artists exhibit in museums and galleries and try to sell work. And what we see here is a 21st century, when the value and the valuation and the presentation of the work moved to the cyberspace. The question is, will this stay with us in the future, and how will that change the art world? Certainly, I'm glad that this could be part of this exhibition.
Ja, lieber Laszlo, vielen herzlichen Dank für die sehr spannende und sehr aufschlussreiche Führung. Meine Damen und Herren, wir hoffen, dass es bald möglich sein wird, Sie hier ins Haus zu lassen, um diese Ausstellung auch tatsächlich real sich anschauen zu können und hier das weitere Wissen entdecken zu können. Die Ausstellung selber ist noch bis zum 16. Januar des kommenden Jahres zu sehen, und in der Zwischenzeit finden Sie auf der Webseite des ZKM neben zahlreichen Ausstellungstexten auch eine Darstellung der verschiedenen Ausstellungskapitel, wie sie hier in der Ausstellung vertreten sind, mit dem entsprechenden Bild- und Videomaterial. Ja, und während der Laufzeit der Ausstellung gibt es auch ein umfangreiches Begleitprogramm, das hier vom ZKM-Team organisiert werden konnte, mit zahlreichen digitalen Panels, vor allem zu Themen wie Epidemic Spreading, Biological Networks, Data Reflection and Design und natürlich zu den Art Networks. Zu den Sprechern gehören unter anderem Peter Weibel, der Künstler Albert-László Barabási, Thomas Saraceno, Mauro Martino, Kim Albrecht, Carlo Ratti und Dirk Brockmann. All sie haben uns ihre Teilnahme bereits bestätigt. Und ja, nicht zu vergessen, am 14. Januar, also als eine Art Finissage, veranstaltet das ZKM The New Data Thinking Symposium, und nähere Informationen dazu finden Sie zeitnah auf der Webseite des ZKM.
Thank you very much, Laszlo, for this wonderful tour. Dear audience, we all truly hope it will be possible very soon to welcome you here in person at ZKM, so that you can discover and experience the exhibition yourself. It will be on display until January 16, 2022. In the meantime, you can find an online representation of the different exhibition chapters on the ZKM website, not only with text, but also with a selection of different video and image material. During the runtime of the exhibition, there will be also a profound accompanying program with a series of digital panels ranging from topics such as epidemic spreading, biological networks, to data reflection and design, and of course, art networks. During the runtime of the exhibition, there will be a profound accompanying program with a series of digital panels ranging from topics such as epidemic spreading, biological networks, to data reflection and design, and of course, art networks. Speakers include, among others, Peter Weibel, Albert-László Barabási, Thomas Saraceno, Mauro Martino, Kim Albrecht, Carlo Ratti, Maximilian Schich, and Dirk Brockmann. Next year, on January 14, 2022, ZKM will then host the new Data Thinking Symposium as kind of a finissage of the exhibition. More detailed information you can find, as usual, on the ZKM website. Now we move on to the digital live discussion with Peter Weibel, Albert-László Barabási, Isabel Mireles and Alice Krushenko on network thinking. We wish you all a very fruitful and inspiring discussion. A very warm welcome to the live discussion of the digital opening of the exhibition BarabásiLab Hidden Patterns. It is wonderful that you're joining us during this exciting evening where we not only dive a little bit deeper into the exhibition contents and the work of the BarabásiLab, but also learn a little bit more about the meaning and the importance of network thinking. My name is Clara Runge. I'm co-curator of the exhibition and have the great honor to briefly introduce our speakers tonight before I pass on the word to the main host of the evening, Peter Weibel. So I'm very, very happy to introduce you to Albert-László Barabási, who is actually located in the exhibition space at the moment. Albert-László Barabási is a physicist and network scientist who changed the course of modern science with his discovery of scale-free networks. He has written and published several books, among them The Formula, Burst or Linked, and he's the author of the award-winning textbook Network Science. In addition to several professorships and appointments at universities like Harvard or Central European University in Budapest, he's also the director of the Center for Complex Network Research at Northeastern University in Boston. The center's main aim is very simple: to think networks. Their research focuses on how networks emerge, what they look like, how they evolve, and furthermore, how networks impact on our understanding of complex systems. The data visualizations he developed together with his lab have been widely published in scientific papers such as Nature and Science, as well as in the New York Times. They have been shown not only in the scientific, but also in the art context, for example, at the Serpentine Gallery in London, or as we have heard before, in a large exhibition at the Ludwig Museum in Budapest, and of course now at ZKM. I'm very pleased to welcome Alice Grishenko, who is a current member of the BarabásiLab and joining us today from Boston. Since 2017, she has worked as a data visualization specialist at the Center for Complex Network Research and is responsible for many of the beautiful visualizations we are seeing in the exhibition. For example, Nature 150, the Human Genome Project, or the 3D data sculptures, just to name a few examples. She received her Master of Fine Art in Digital Animation and Interactive Media from Ohio State University. As a design generalist, she has experience with illustration, animation, data viz, game design, and of course, virtual reality. Then I warmly salute Isabel Mireles in Toronto, with whom we have another data visualization specialist in our round. Isabel Mireles is an information designer and since 2015, a professor in the Faculty of Design at OCAD University in Toronto. Her interest focuses mainly on the relationship between visual thinking and visual representation. Her research examines how information is structured, represented, and communicated in different media. Isabel Mireles is author of several articles and books, such as Design for Information, an introduction to the histories, theories, and best practices behind effective information visualizations. This was published in 2013. In addition to writing widely on the role of data visualization in society, culture, education, she has organized numerous conferences and exhibitions on the topic. For example, she has curated the exhibition The Art of Networks at Fusana Art Museum in Melbourne in 2012. Finally, I warmly like to welcome our host of the evening, Peter Weibel, who is also in the exhibition space and who is the curator of the exhibition and the artistic scientific director of ZKM Karlsruhe since 1999. Before we start the conversation, a quick reminder. If you have questions during the talk and the discussion, please feel free to add them in the YouTube chat or in the comments next to the Facebook live stream. I'm very happy to forward them to the speakers at the end of the talk. As you have probably already noticed, there are two live streams at the moment, one in English and one with a German translation by our amazing and certainly well-known interpreters, Leonie Wagner and Sonja Willner from Baden Dolmetscher. So, dear Laszlo, maybe I may start with the first general question. You are one of the leading figures in the world of data science and often called father of network science. You also have an artistic background before studying theoretical physics in Bucharest and Budapest and earning your PhD in Boston. You actually studied sculpture. one can observe that throughout the years, you brought your scientific practice closer and closer to the art world. Can you briefly tell us your story? How did you find yourself working in the field of network science? And what role does art play in your and your lab's practice?
Well, first of all, Clara, thank you very, very much for the opportunity being there, and both to you and Peter Weibel, who made this exhibit possible, and for the countless hours that we spent together to make this reality. And indeed, my story kind of starts way in high school, where I was studying mathematics and physics, but I really became fascinated with sculpture. And my father was a museum director and a museum of a school as well, which was focusing on art. And I took advantage of those opportunities to kind of study art and study sculpting and drawing what was necessary. But at the same time, I was fascinated by physics in particular, and eventually the reality of the Romanian education system had pushed me towards becoming a scientist rather than an artist. But it was a love that stayed with me for many years. So when I became an assistant professor at the University of Notre Dame, at a relatively young age, I was 27 when I arrived there, I have taken advantage of the courses offered by the university and the right as a faculty to take free courses. So I had the chance actually to listen to the art curriculum at the university, from practice, actually from black and white photography, lab work, all the way to some of the theoretical courses. And interestingly, this was the same time when our interest, my lab's interest, has significantly turned towards networks, and we started to publish networks. Spending much of my free time on galleries, museums, as well as in the art department, and doing science on networks kind of led to an accidental convergence of the two journeys. That is, that the desire to really represent our scientific findings in a visual way, to kind of develop a visual language of network science. And it is this 25 years journey that has kind of been now represented here at the ZKM. And hopefully, if those who have a chance to kind of visit will see not only of how we represent science, but also the evolution of the language.
Great, thank you. Maybe I would like to turn over the conversation to Peter Weibel with a follow-up question. The exhibition BarabásiLab Hidden Patterns was planned as a takeover from the Ludwig Museum. In the end, the outcomes differs not only because of the spatial conditions here at ZKM, but also because it was possible to include some of the new, recently published projects of BarabásiLab. As the artistic and scientific director of ZKM and the curator of the exhibition, how did this project catch your attention in the first place, and why is it so interesting for an institution like ZKM?
Thank you, Clara Runge, co-curator of the exhibition. It is my great pleasure and privilege to welcome you tonight to this kind of virtual opening of the exhibition BarabásiLab Hidden Patterns. And it's also my great pleasure and privilege to welcome you to this virtual conversation with very important and excellent experts like Isabel Mireles, Alice Grishenko, and naturally Albert-László Barabási. I will use this evening and discuss several questions about visual representation, visual thinking, and network thinking. And I will jump from these different participants. Therefore, since Laszlo already has talked about this lab, I would like to ask Alice Grishenko. Since 2017, you design as a BarabásiLab and responsible partially for many of the beautiful works we see here. Therefore, my question is, can you give us some insights from inside the machine place there, how these processes with beautiful results we see here are developed, and how this network visualization is created, with what kind of mathematical tools, graphical tools. So please give an insight in the machine room of the BarabásiLab.
Thanks. Sure. So I think to start answering that question, it's valuable to note that network science is sort of inherently visual, that networks, the data makes them. It often starts off in like a table or, you know, in some sort of file, and that it's not a network until you draw it, really, you know, and you can draw it in many different ways. And so in some ways, you know, it's sort of the visual is inherent in the study. And I think there's a lot of different ways to connect things, but that's sort of what it's about, is where are you drawing connections? How are you encoding the information related to both the connections and the data being connected? And sort of how many visual dimensions do you have to share that? You know, you have spatial dimensions, maybe 2 or 3 if you're working in some 3D software. You have like color and size, and you know, how can you know, shape. You can add a lot of things to it, but it's sort of about taking the narrative and communicating it visually. And you know, we'll use a lot of different tools to do that. The process is generally that there's a lot of pre-processing of the data by researchers, a lot of researchers, and a lot of work in the pre-processing of the data. And that then once we have a narrative, we can start to make those decisions about how to encode the information. And then it's a highly iterative process. You know, we try a lot of different things, we see what's working, and we kind of go from there.
Okay. Isabel Mariles, you are really an expert in the history and theory of communication design. Please can help us to the benefit of our audience to explain us the differences between one side visual representation, as the other side visual thinking, and now finally this new terminus technicus, network thinking. What are the differences between these 3 termini technici?
Thank you. Thank you for having me. It's like amazing to see the exhibit. I hope I can travel there and see the exhibit. Let me first start by saying that it's, I think as both Laszlo and Alice pointed out, the whole idea of networks connects to thinking and visual thinking, and because it is about the connection between the elements and not the elements themselves. So basically, I think there is a lot that the representations can do for the thinking. I think network thinking is somewhat different from visual thinking. I mean, of course, they connect through the visualizations or the representations, but basically, I think Alice pointed to something that is quite crucial, that is the visual thinking that goes with thinking about networks, and how in the process of the network science community, how the visualizations have played and still play an important role in the science. And so in the presentation of the exhibition, Laszlo was saying how many of the images in the exhibit are actually never been published, and yet they are so important into the thinking and gaining insights and knowledge, so that other new questions can be asked of the science as well as the representation. So I think in that particular instance, there is an intrinsic connection between visual thinking, the network thinking, and the visual representations of the network. Yeah.
I think we have learned in the history of humanity to represent the world. That means objects and living creatures, to represent the world by words. So we have language. We have written language and spoken language. These are 2 kinds of codes. Then we have learned to represent the world, objects and living creatures and organisms by images. So this is what we call visual arts. Yeah? But now I think we have a new step in the evolution of humanity. We are representing data. Yeah? And therefore I ask all 3 of you, what is the difference between the representation in spoken words, written language, and visual icons, symbols, and indexes, and now with data? Is it difficult to represent data, is it difficult to make a relation from data to the actual analog world? Laszlo, what is your experience on all of three of you? What is your experience on your theory? Yeah?
Sure. Since you kind of pointed, this is a very interesting question because I think of our work as being very deeply rooted in realism. And it's kind of odd to say that because we're used as realism as, very realistic paintings of humans and the landscapes and things like that. But and realism means a fidelity to the object that we try to show. And in data visualization, we have to have a great fidelity to the data, right? So like we must actually follow the data and we must represent as it is. But at the same time, there is a curation process because it's virtually, you can never represent the whole data. You're lucky if you can do so. And when you do restrictions, you must do it with care and you must do it also with a storytelling in your mind. So in a way, I often think that, like if you are a painter, you have fundamental restrictions of your medium. You have to paint on 2 dimensions, you work with paints and so on. If you are a sculptor, you have other type of descriptions that you have to observe the materiality of the stone or whatever you work with. In the same way, our restriction is the fidelity to the data to currently represent the data. But once we agree to do that, we have quite a bit of freedom of what kind of visual language do we choose. And I think that visual language hopefully is very much a display at this particular exhibit, that we have choices. And those choices are often decided of how do we tell the narrative? How do we tell the story? I tend to think that data visualization is always a storytelling. And that's kind of the reason I kind of perceive this particular exhibit and the whole process of what we do in the lab, that these works have to work simultaneously at the 2 levels. They need to work as an aesthetic experience, but they need to work as an intellectual experience as well, if you're willing to penetrate and think about what is being represented and how is the data being used to kind of tell a story.
Isabelle, is data visualization a new code, a new language, a new kind of communication? And is it difficult for normal people to understand this new code and language? What is your experience?
Yeah, I think I have to agree with Laszlo that most visualizations are about storytelling. And I think that, I don't know if it's a new language, but it's actually something that it's in the boundary of the data or what is we are trying to represent and how the people on the other end are actually trying to interpret. And so it's always schematic. It's always involves, some code, right? Someone that is actually decoding what has been encoded into the data. And so there is this process of standing for. So there's always a proxy, there is always a connection between the visual elements, whether they are 2-dimensional, 3-dimensional, what they stand for in the data themselves. And so I think for that, there is a need to convey for the people who are in that regard. There are also metaphors that we can use. So there is a lot of visual thinking and cognitive thinking that plays a huge part.
Difficult for people to understand this sort of new language of visual communication or data visualization. And I think it should not be, maybe initially, you have to learn
Hello and welcome back. We really apologize for this technical issue. All of a sudden the internet connection was gone, but we are back and we hope you remind the question Peter Weibel just asked to Alice, because it was really interesting, and I hope Alice, you still have the thought in mind and can continue.
Yeah, of course. So the process for, how to design a piece, a data visualization, I think often starts with sort of saying which dimensions of the data are what we're focusing on. Often you have many things and you have to choose what's important to represent. And then also you have to match which attributes you're including to which elements of the visual. And I think, part of this question earlier, as when Isabel was discussing it, is will it be difficult for people to understand this new form of communication? And I think, it should not be in theory, because that's the idea, is you're designing something for people to understand from the image. So I think sort of beyond the initial introduction to representing data in an image, it should be pretty clear to follow with the codifications. And yeah, I mean, I think on some level, representing, all of the systems you described do represent data, but that the data is also an abstraction of reality, that you're recording these numbers, which is like a measurement of something, that the tool also changes what the number is. So it's sort of this many levels of understanding and codification. And I think, people just build these systems on top of each other and use one to understand the other.
I think too, there's a big difference between representation of data, because it's a kind of ontological jump. Language and images have been representing objects and living organisms, but now we're representing data, which is a higher level of abstraction and of symbol processing. For coming back to the history of visual communication, like it was developed in Vienna by Otto Neurath, the isotype, or like it was developed in Bauhaus, in Ulm, and in Dessau, etc. And there have been many people from Brazil and from Argentina, like Maldonado, who came from this German tradition. But my point is that normally visual communication is just a mirror of the actual world. And now we have this claim as a BarabásiLab, with a new network thinking, with a new way of representing data, we discover something which we did not see before. We discover hidden patterns. So the history of visual communication did not make this claim, did not say we have an epistemological value. It's an instrument of knowledge. That we discover hidden patterns we would not discover without this new representation of data. László, do you see it correct in your work?
I certainly agree with that. And I think what Alice has said was very important, I think, is that we tend to speak of data visualization as is the goal is to visualize data. That is not the goal. The goal is to understand reality. And data is just an intermediate layer between our understanding and reality. And I said we have to have fidelity to the data. What I didn't say is that the fidelity has to map into the real world. And what data allows us, indeed, coming back to the hidden patterns question, is to really discover linkages that are not apparent to the people, even those people who are part of the system, who are experts of the system. And, a good example is the art network that is currently exhibited over here. The institutional links of how the different art institutions are connected to each other some of them may be obvious to some of the people who work on those institutions, but the global picture was missing until we were able to use large data to map out how 20,000 institutions, art institutions, connect to each other. So what the data allowed is to discover these hidden linkages. And then what the visualization allowed is to bring it back to the user, to the artist, to the art historian, and to offer a new perspective of how the artwork really works. And if the data visualization doesn't offer this new perspective, then it's a lost opportunity. And as Alice said, it has to communicate very well. And the way I often kind of format it, and I remember that I first formatted in my lab in 2001, so exactly 20 years ago, that most of the work that we published on data visualization or any type of visualization came in research papers. And I said, a good visualization works at two levels. It works as a figure in the research paper, but it has to work when you take it out from the scientific context and you leave it alone. And it should have a content like that as well, so out of context. And when I consider a success of visualization process, when we achieve that meta-knowledge, that meta-representation, that it has a life on its own, even when it's divorced from the scientific context.
I think this is an important point, that network thinking has a new claim in the history of different kinds of languages. And what I see in this exhibition and your books, you use your method of data representation, network thinking, in the topics of traffic frequency, in topics how to discover structures of the cosmology, structures of the brain, even using these methods for network medicine, even in molecular realm, and many other areas of science research. Does it mean, two questions, we are closer to the dream of mankind of a kind of universal language? So network thinking is a new step, inventing a new universal language to treat independently different areas. This is my first question. And second, like in network medicine, is this promise correct that with help of this new network thinking, we can have new solutions for problems we have in medicine, for problems we have in cosmology, etc.? Is it really possible to think that we find not only new patterns, but also new solutions with this kind of new universal language?
Well, if I may just very briefly, I tend to think of that we're not inventing the network language, we're discovering the network language that's already in nature and technology. And I think that the real reason, the real power of the network thinking comes from the fact that these systems that we are representing work as a network, right? Life is not a set of genes and molecules. Life is really about the interactions between those genes and molecules. Society is not simply a phone book of the list of people living in the city, but it is actually the interactions, the working together, the family, the social links between them. The economy is really not about products and sellers, but it's about the transactions between the maker and the buyer and so on. So the systems that we represent in this exhibit and we study in my lab are inherently organized and function as networks. And what network thinking provides is a way to bring back and visualize and to help us understand that underlying mechanisms that make the system works in the first place. So that's why I tend to think we are not inventing it, we are discovering it, we are rediscovering the tricks that nature has already invented tens of thousands or billions of years ago, depending on what system you look at.
Isabel, do you think that this emergence of network thinking is a new kind of visual language? Can it make a bridge between art and science? Because normally, say, an analogy between visual structures in art and visual structures in nature have been more and more superficial. It was a kind of visual analogy. But do you think that network thinking really can make a serious bridge between artistic, science-based artistic processes and truly scientific processes, so to make a new bridge between science and art?
Yeah, thank you for the question. Yes, absolutely, I think it can make and it makes actually an incredible connection between the arts and the sciences, not only for the power of what the network science brings in terms of thinking, in terms of discovery, as Laszlo just pointed out, but actually in opening up new imaginations of artists. And I remember when I think I'm not alone, I've heard different artists and designers actually the power of having linked the book. I even brought my copy here so that, just it was incredibly influencing reading and understanding what we're facing, and that Laszlo actually wrote for all of us to kind of understand, and helping us bridge the science towards all of our own individual disciplines. And I think coming from the arts and design, I believe that absolutely there is this connection. And of course, we can think about artists throughout the ages who have been or who have thought about network thinking and actually using real words. And I'm thinking here perhaps of Mark Lombardi's drawings or Hans Hacke, and I think that by bringing the work of showing 25 years of actually all the visualizations at the BarabásiLab, we are actually able to see it in a broader and the influence that it actually has played in different disciplines and in the arts. Yeah, I think there will be a lot more that we'll see in this, and I believe that actually by exhibits like at the ZKM and Budapest, the influence and the understanding of the connections between arts and science will be even broader.
So could we say that all these famous terms like pictorial term and like iconic term, we have now with visual, with network thinking, a kind of cognitive term, that we've now developed visual tools really to understand better than before reality.
Yeah, absolutely, absolutely. I don't know if Laszlo wants to join into that. Yeah, but yeah, or Alice. Yeah, I believe that and I think visualizations are this beautiful artifact that actually connects. It's kind of in the interconnection between the arts and sciences as well. And so, yeah.
Now, I think it's very evident because we have the history of color and form in the normal visual art. We have the famous, for example, interaction of color by Albers. But now, as Barabási explained, we have the interaction of parts and elements, what you call linked. Now we see there's a kind of theorem of inseparability. So in a network, everything is linked to everything. And so we have now a new way, not just think about interaction of color, no, we think about interaction of data. This is really much closer to reality than just interaction of color. But I have the question, Alice, what are the tools, the mathematical tools, when you make a work, Alice? Do you have to learn every month a new mathematical field? Do you have to learn every half a year new mathematical physical tools? How do you proceed to be updated in the technology to develop always new tools for a better network thinking? So I have this question to both of you, to Isabel and to Alice.
Well, thankfully, I work full-time in CCNR in a lab full of data scientists and researchers who, do a lot of hard data processing and math work. So I think, I get exposed to a lot of data analytics conventions. I get to learn about those from seeing them work on them, but truly my side of the process is really learning which technologies can be used to deliver what type of visualization. We work with a lot of different things. We have still images, we have 3D structures, we have interactive pieces and animated pieces, and sometimes it's a 3D animated piece. So I think just understanding what the options are to make to deliver it in the best possible way, and that those are always changing. So yes, you do sort of need to keep your eye out for the newest softwares or software updates or packages, but I think that's a very fun part of the job, is seeing how things develop, checking them out, seeing if they work for you. So I think it's not so bad.
Isabel, what is your experience? This kind of visual patterns created by mathematics and data representation. Do you think in our present time it is easily accepted by the art world? The other question is to László, this kind of visualization and this beauty, is it easily accepted by the science community, or is it still a little bit difficult?
Yeah.
First, Alice, please.
Well, I think in general, it depends on which part of which community. In research, I think generally people are very supportive of interdisciplinary collaboration. I think from sharing methodologies with each other, you learn a lot, and you know, people who are doing research are excited to learn new things. So, but then perhaps maybe as you go away from that into the maybe more corporate areas, I think those places are sort of, they build, or it depends where, but sometimes you'll find these niches of people who all work around their methodology, all of the infrastructure set up around their methodology. So it's not very welcoming to, you know, information, like the scientists, maybe it would have a harder time to collaborate with artists or vice versa. But I don't think that they necessarily don't want to, you know, it's just sort of maybe inconvenient. Yeah.
Isabel, how is it in this field of art?
Yeah, I think visualizations are now common ground, I would say, and they have played an important role in many areas, not only in the sciences and in design, but actually, if we see this past year with COVID, I mean, we were exposed to a huge number of visualizations in the media. You know, actually, perhaps even, you know, we got even stressed of looking at so many visualizations and kind of looking and understanding what was going on in the world around us. And so in the arts, we've also seen many visualizations for a number of years. So I mentioned Lombardi in the 90s, or, you know, others. And I think what is important, perhaps, I think more than anything, is the context. Why is it that we are actually creating the visualizations? For what purposes? And for what expression, and what are they communicating? And I think to go back to the exhibit, to the hidden patterns, what for me is most striking is the way that it's been used in the lab, and at least in my, you know, experience of participating in the lab and experiencing people designing there and the scientists working on the data, is actually using that to think through, to gain insight, and eventually to even ask further questions about the data themselves. And so I think in that regard, what is phenomenal about having an exhibition such as the one, the Hidden Patterns, is actually exposing to the larger public that might not have that understanding of how much visualization plays a part in the scientific thinking, and how much it actually is used not only to communicate the findings in such a way that we see in the covers or in the papers, but actually in the process of thinking and in the process of discovery of these complex systems.
László, your cover.
Yes, I tend to think that the word visualization doesn't really cover of what we do, right? Because what we do is searching for the form that best represents the underlying reality. And, you know, when we look at visualizations, people tend to think of two-dimensional images of something. But if you come to the ZKM exhibit, you will see light boxes and two-dimensional images, but you will see three-dimensional data sculptures. You will be exposed to augmented reality. You will see networks laser carved into glass cubes. You will see a whole range of materials. And these are not by accident, because what we really do in the lab, and what Alice has been really fabulous about, is to really keep searching for the form, for the material that best represents the reality that we would like to show. And it's no one size fits all. We now also have lots of experience of what kind of materials you want to use for certain type of messages, but we are always learning and exploring and designing and working with others to find others. And if anything, you know, Alice is a little bit understating her role in this process, because she's saying, oh, it's about visualizing data. No, it's about finding the material. When she joined my lab, it's fair to say that she hasn't done any three-dimensional sculptures before. Neither did she, nor did I, right? But now she's an expert of how you actually do 3D printing and how you lay out a network in 3D space such that it's actually printable and so on. And that was a long learning process that we have actually done together. The Budapest exhibit, we have a giant virtual reality platform actually, where people can go inside the art network and interact and see who are the nodes and so on. So I would actually characterize the journey that is being displayed here at ZKM as part of the underlying research of the lab. It's part of the research mission, is to find the materials, to find the forms that really best represent the data we would like to show, the story that we would like to tell. And this is for me where the interaction with the art space is so inspiring. The way I actually visit museums and galleries is that I always looking for the form of representation, the materials, the techniques, the tools, the ideas of how they get certain messages out. I take photos of them and I bring it back to the lab and we discuss them and we say, could this be actually ideal for that particular project? And this is what I often call the inverse appropriation process that my lab practices on a daily basis, which is we are used of the standard of proposition that ordinary objects from the regular world are being put in the museum space, in the artistic practice, often coming from science, often from just ordinary objects like, you know, the pissoir of the famous pissoir from 1919, right? And we have an inverse kind of appropriation where we are inspired by the wide range of representations that are present already in the art world, right in ZKM today. I just visited the world space today. It was a fabulous experience. And then we say, which of those forms of representations, which of those vocabularies are ideal for one of the projects we are just working on? And if they work, we bring it back. We learn from that. We appropriate it. And we use it as part of telling our story built into our narrative.
You described very well the reasons why I was interested to cooperate with the Ludwig Museum in Budapest or to show your work and your research here at ZKM, because it offers a new kind of science, but also a new kind of art. So it's a pioneering achievement for the 21st century when we are entering the century of data, etc. And the reason why I think it's a new kind of science and a new kind of art is the following. Because in the 19th century, from Laplace to Maxwell, scientists have been proud to use no diagrams, to use no drawings, to just say in the preface, this is work of real science because we have only algebraic operations, only numbers. And now the cover of your work of the Nature to the 150th Jubilee of Nature, the most important scientific journal. So that they allowed you to present their own data as visual is very interesting, because they realized it is not just an ornament, because normal scientists always think visual things are just ornaments. They are not really useful tools of cognition. But now that it's a real paradigm change that you have been invited by Nature, this wonderful magazine, to create a cover for the 150th Jubilee. So it's very clear, science understands that there's now creating, by network thinking, a new kind of science. And the same, I think, will happen in art. Therefore, for me, it was important to show it at ZKM, Center for Art and Media, to show that we have now new tools, which have been described by Alice very well, and by Laszlo, new tools to create a new kind of art, not just a visual, interesting, fascinating, beautiful forms of color, etc., but also a kind of what I would say noetic turn. So suddenly it can be the case that what we see it's a new story which is told to the brain. Because normally in art, there's a lot of things to see, but not so much to think about. But now we realize it's possible that we have to think more about what we see. This change, that in this exhibition, it is so stimulating because you learn, I have to think much more. I have to think beyond what I see. And normally when you go to a museum, it's just the opposite. You see more that you have to think. And therefore, I would say, I'm very grateful that we had the opportunity to introduce this new way of network thinking to Europe together with Hungary. So Clara, maybe you have some questions?
Yes, it's really a good moment because we have a quite vivid public, so I'm happy to forward some of the questions. We learned a lot about the positive effects of data visualizations, and Philip wants to know, what do you think about the cons of data visualization? For example, in regard of estimation versus accuracy, or how does one measure whether the data scientist and designer actually understands the data involved to a level that minimizes overt or unintended descriptions? What do you think about that question?
I would refer that one to Isabel. She wrote a book about data visualizations. Yeah. I wonder how you think about that.
I think it's a hard question, quite honestly. So I think as with any kind of tool, there's pros and cons. I think the important part to think about is everything that we do in visualization or in design actually has a compromise. And so it's important to understand what that compromise is about and how that actually plays a part in what is being conveyed. And so there are many cons as much as there are many pros. But I believe that one of the important parts that I think that especially visualization in particular are good at is actually giving the broader understanding, the big picture of it. And I think node link diagrams are specifically good at that. And then on the other hand, the cons would be, it's hard, given some density of network, for example, it's hard to understand what's going on because of all the occlusions, say, for example. But the question is, to what extent these play a part, and if we can learn about these things that are occluded, say, in other forms of visualizations or looking at other ways of representing. So I don't know if Alice would like to add anything to that.
Sure. So I think on the data analytics side, there are some mathematical and analytic ways that you can check your error, and you can compare the numbers you're getting from the code you've written to real data and sort of have a quantified check of your margin of error, which is nice. It's probably not infallible, but it's one way to do it. I think another thing that we really commonly do is talk to an expert in the field of whatever the data is about. If it's publication data, maybe consult a bibliometrician, or if it's, data about biology, talk to bioinformaticians, or if it's genetics, talk to a geneticist or genomicist and ask, how does this compare to what you were expecting to see or to what you are familiar with? And just make sure that there's consistency in your interpretation and their interpretation, or if there isn't, discuss why that may be. And I think those are you have sort of a quantitative approach to doing this and a qualitative approach to doing this. And, you just try to check it from as many angles as you can.
Mm-hmm. Yeah. If I may just add one short thing is that we are not a data visualization lab. We are a scientific lab, and our reputation is at stake when we visualize, right? So, and hence, that's what's special about here. We don't only have Alice. Alice is embedded in 30 scientists group, right? And everything that kind of comes out is checked whether can we put actually our reputation at stake by being properly represented. We know that visually you can create lots of illusions. Our goal is not to actually to create illusions. Our goal is to capture reality.
Laszlo, how many people work in your laboratory? Huh?
About 30 people, and we have actually, as of last week, we had 2 designers, Alice and Suyu, and we're about to hire another designer. And so most people are actually scientists, but right now about 3 people among the scientists are also work on the mathematics of the visualization problems. How you use AI to visualize, how we use AI to choose colors, how we map out the artistic space and so on. So there is a lots of kind of conversation even among the scientists about the art space, and they are getting more and more involved in developing new tools and techniques.
I think it's very important that this evening was made very clear. So your work and what you see as exhibition is not about visualization. It's not about data visualization. It's much more, it's a noetic and cognitive and epistemological tool. Therefore, I dare to ask some philosophical questions to Isabel and to you. There is this also famous Hungarian Nobel Prize winner, Denis Gabor, who invented holography. Yeah? So it's about, he's one of the major thinkers about holistic approaches to the world. Yeah? And therefore, and we have also another one, David Bohm, the quantum science physicist, who made a book about hidden variables. You speak about hidden patterns. Yeah? And he was influenced by this idea of the holon, the whole, that the part is only a part in a certain circumstance, but it can be a whole for a smaller part. Yeah? And the smaller part can be a whole for again smaller part. Yeah? And the whole can be just a smaller part for an even bigger whole, etc. No? This kind of holistic thinking here, which led by David Bohm to the idea the world has a lot of hidden variables. Do you, Laszlo, feel you close to this kind of thinking, or is it something very different here?
It is, and I would say that network science has kind of answered an answer to many of these questions that were really posed decades before, from systems theory to what you actually mentioned. So network science is really trying to open up the box and make the invisible visible, right? And by going back to the data and trying to understand really where the data comes from and how you represent it. But at the same time, we stand on the shoulders of giants, right? And many of the ideas that we are actually exploring now are really rooted in the opportunity that we can realize many of the programs that both scientists and artists have formulated. You and I, Peter, had lots of wonderful discussions about how our work in a way continues what George Kapesh has started at MIT, right? It's a natural continuation, who was one of the first artists to take artifacts from the lab and put it out as an exhibit, mostly for the formal correspondence. But you could actually see the BarabásiLab's work as being a natural extension where we're not happy with the formal correspondence. We are actually looking for the conceptual, the content-based correspondence, and bridging the gap between the content and the form, and making them to work together in a way that they are not divorced, they are not a gimmick, but they're part of one whole.
I think it's very clear what we could say to understand better what you're doing. You're a new way, a new solution of the old holistic thinking and the old system theory. So it was very good steps. We had system theory, we had holistic philosophy, but now we have something higher, which is called what you call network thinking. Yeah? And I also would therefore say, since the title, A New Kind of Science, comes from Stephen Wolfram, a big book about digitization. Yeah? Could you also say that you are part of a new kind of digital philosophy? Yeah?
Yes, and this is very much in the air. And I think what has happened, and this is where the data piece comes in, right? What the ability to kind of collect data at a massive scale allowed us to peer inside the systems and look at them in such a detail that it was not possible. And whenever there's a technological advance, and I would say big data is a technological advance, then you are entitled and you have the platform to make a conceptual, a philosophical approach, because it makes things possible that were not possible before. So I really think that the big data thinking will result really, and does result in a much higher level holistic approach, just because the invisible became visible.
Yeah, I think it's very good. With the new technical, digital, and mathematical tools, we are on a high level to realize hopes of these classical ideas of holistic approaches and systemic approaches. I think that's very interesting what you said, that with new tools, digital tools, new mathematics, that we can come closer to reality. No? There's this wonderful book called Road to Reality. I think with network thinking, we are on a new track, on a new road to discover more about reality than before. So Isabel, would you say you could experience something similar?
I think what, you know, I was thinking about what Laszlo had just said as well, Peter, that about the hidden patterns. And eventually, you know, I think one of the amazing possibilities of network science, at least, you know, Laszlo, correct me if I'm wrong, but basically is also the hidden, because we don't see them. So for example, when Laszlo was describing the connections between the museums, so we see where the museums or the artists or the institutions are located, but how they are connected is invisible unless we ask the correct questions, or unless, you know, those connections are mapped in certain ways and then visualized, of course. And so in that regard, I think it is the whole new way of thinking in terms of the network thinking for me. So it's like, sorry to bring it back to that. I was still thinking about what Laszlo was talking, so I don't know if it actually makes sense, Peter. So, yeah.
Clara, do we have another question?
Yeah, I would like to add a question of Marie, which fits maybe quite well. And because you were talking of the overview that, yeah, network science give us to over the hidden patterns. And she's asking if that is a chance that empowers us to influence or even change the network they reveal. And if so, how?
Well, knowledge always allows you to influence, and not only that allows you to influence, but you have a responsibility to do so, right? Because the reason we want to discover the patterns and the laws of nature is that so that we can make our world better. And we do want to be actually activists. For example, my lab has just finished a big work about looking at the different patterns, women artists and men artists, different trajectories they have through the artwork. Why do we do that? Because we want to create opportunities for communities that are underrepresented in the art space. We are trying to understand the subcellular network because we want to design better drugs. We want to find drugs for COVID. This is one of the projects that actually is being displayed just behind me. These light boxes that you see, the glass boxes are really the drugs that we discovered and tested experimentally to work for COVID. So indeed, the purpose of the science and the purpose of the visualization process is to open up new opportunities. And we're not shying away from that.
Another question?
Yes, another question is more referring to the topic of the different media your lab is using. And a person without adding a name was wondering if you have any thoughts regarding the possibility of auditory representation of networks, perhaps giving us a different understanding that are not sufficiently represented via the visual.
Oh, I would love to. And Alice, please do take notice. This is something that we have to go in that direction. But I think you worked lots with the kind of different theater groups before you joined the lab. Do you see an opportunity for us to go in that space? And how would we do that?
I think that's a good question. I think it requires, you know, maybe a bit of in-depth thought about how to actually do it. But, you know, I think my first thought would be, you know, that with a lot of, for instance, like the virtual reality applications we make, there's, you know, you have 3D sound in the digital space. So that already, you know, adds a dimension. I could see, it really depends on what the data is, but if you have audio data, you know, if you have audio data already, you could attach it to the digital space. You know, you could attach it to the nodes. It could be clips of people talking if the nodes are those people, something like that. And I think, you know, sometimes we embed videos in our interactive projects. So in that sense, in that way, associated, but I feel like you could also be very, you know, a bit more experimental and generate sound from data. And then of course, I mean, that could go a lot of different ways.
And I also feel that we can be inspired by art. So I loved the Palais Tokyo exhibit of Thomas Saraceno, where he had these giant networks that you can play with and they would actually emit audio sound. I just learned yesterday that concept was developed by Thomas here at the ZKM with collaboration with Pippa Weibel and his creators. So that's, like this is yet another example of artists have discovered ways of communication that we can appropriate and fill it with content from the data. And I don't think we should shy away from that challenge.
I have a technical question maybe to Alice and Laszlo. When you make a line, so it means you make a line between one point to the next point. And normally we call it in mathematics a directed graph. How do you spell it? Graph or graph? You know what I mean? Graph theory. So is it something in your work, Alice? Can you use very complex graph theories to make a network, or is a mathematics by a network completely different?
To be honest, I think, as I said, I work with a lot of data analysts who are applying these complex kind of mathematical models to the data. And sometimes I, do some post-processing on the data afterwards, but I would say probably, yes, these are graph theory is being used. I myself do not really work with that side of it.
I have another question to Laszlo and to you. You know this famous so-called, Darwin made one drawing in his book about evolution, and it was called the tree of life. But we know it's not a tree, it is a coral. So, but in fact, you could say today this coral, how much a drawing is a drawing of directed graphs. Do you think that when you're very advanced in network thinking, we can also find new models of evolution, Laszlo? Can we hope so?
Oh, very much so. And actually, my lab has been involved a little bit a few years ago of trying to map and compare the different networks within different organisms and try to really understand different aspects of evolution. Because indeed, traditionally, the genetic evolution is described as a tree, as if things start splitting, but there is but the tree is really not a tree. There are lots of loops in it because there's lots of what we call horizontal gene transfer. So tree is a simplification of the reality. Life always steals from each other, right? From the one organism from the other one, different mechanisms, genes, and kind of perfect it for their use. And in a way, this question that you ask is one of the questions I would like to answer. We would like to use network tools to answer these deep and really fundamental questions about the life, about universe, about society. So for us, the visualization and the scientific journey is not the end or the goal. It's a means towards really understanding the world around us.
So what you just said correctly about the interdependence of smaller and bigger living organisms from cell biology, whatever on. So today it is called holobiontic elements. Are you also working in this direction of mathematical models of holobionts?
Not momentarily. We had about 5, 6, 7 years ago, actually, a project where we kind of encountered that. And what also has to be kind of, perhaps didn't come out clear, that everything that you see actually in this exhibit are deeply tied to research projects that the lab has spent years and often as long as a decade researching. So we are not, let's call it a visualization team for hire. We only can engage in projects that really expertise-wise fall into the intellectual journey of the lab. So every project that you see here also have research papers associated with them. And the visualization was a symbiotic process of the research process. It's just one, in the same way as you just mentioned, graph theory is one of our tools, you know, and the differential equations, and you name it, are one of the tools. So is visualization. It's a tool to understand the complex systems that we encounter.
So I have the question now, these projects, I have the impression, László, that on one side you invent your own projects, you propose projects, and from the other side people come from outside and propose projects to you. Is it true? Is this a mix from inside and outside influences, or is it completely different?
Many people kind of suggest projects for us, and I would say on a weekly basis I get actually emails from people to say, oh, you are on network sciences, you're probably interested in that. I would say 90% of the time they're right that the topic is interesting, but the project doesn't fit us. Because the question is, are we breaking new ground? Just for us to analyze yet another network doesn't really excite us, right? The question is, will we gain new type of knowledge? Are we going to further the understanding of a system in a meaningful way? And are we also going to further network science and the tool set that we have in a meaningful way? So we always try to be kind of at the bleeding edge, find that place where if we do something, we not just understand the system, but we further the whole discipline. And often what I find is that people, when they suggest projects to us, they look at some of the older projects and they conclude that therefore the new project would be interesting for us, not understanding that that older project is already done. We don't want to do another one like that. We want to find the next frontier. So for example, for many ways, the next frontier for us is art. By meaning that use data to understand the process of art, that we use data to understand the mechanisms, the social aspect of art, the way success emerges in art, to actually infuse into the art world the use of data, the data-based narrative. That, for example, is a very bleeding edge project because very few people have kind of taken that perspective. And there is a transformative opportunity for a discipline, which is a discipline of art, by bringing these tools in there.
You just mentioned the word network science, which I like very much. Could they say, László said, network science, network thinking will have an influence in future on all kinds of different other scientific areas, like medicines. We can expect a lot of networked medicine. We can expect a lot about traffic theory from network traffic theory. So can we say the network science is a foundation with a big of influences in other sciences?
I really hope so.
Okay, so Lara, do you have another question?
No, I think, yeah, there are some more questions, but with
how much time do we have?
I mean, we are already like over time, but maybe we can stop with one last question to conclude this very interesting talk. And Tom just asked if you think if the physical world can be described in terms of networks as a theory of everything, like Wolfram Physics project.
No, there is no theory of everything. As a scientist, I really need to kind of focus on the particular problem at hand. And I'm not a believer that there will be one meta theory that would describe everything. And to be honest, if we find such a thing, it would be really a sad moment for science.
Okay, as we are over time, Clara, we are over time.
Oh, I mean, we planned 1 hour for the talk, and yeah, we're more or less, yeah, we're there. But of course, if there's still like questions or things you like to discuss.
But we have answered questions from the audience.
Yeah. Yeah.
Okay, then I would say I was really happy that I would welcome Alice Grishenko, Nisa Mireles from Boston and from Toronto. It was a really wonderful, exciting opportunity to share with us your expertise and your knowledge. I'm very grateful that you joined us in this conversation and that we really can learn from your experiences and knowledge a lot. Thank you so much. And naturally, I'm very happy that László Barabási is here in the home. So I'm sitting in one room, he's sitting in another room. So it means we have now 4 different locations. Clara is sitting in another room, so in another rooms we have 6 different locations. The same with many visitors which are globally distributed. So it's a wonderful event. As I said, we can make a conversation in a virtual space, unified in a virtual space. but linked, precisely linked. So we have practical examples of network science here. Thank you so much.
Yeah.
Thank you for being here.
Yeah, also from my side, a big thank you to all of you, to the 4 speakers. It was really inspiring and great that you gave us insight in your thoughts. And I think also that it was a great starting point, and we will definitely keep the discussion going in the context of the accompanying program of the exhibition, so we can keep discussing. The series of digital panels, mainly organized by Teresa Rezza, will start with the topic of epidemic spreading. On June 3rd at 7 p.m. So please have a look at the ZKM website for more detailed information. And there you can also find, of course, more information about the opening regulations of the museum. So we all hope that it will be very possible soon to welcome you here in the exhibition and in ZKM in person. At the end of the evening, I quickly like to take the opportunity to thank all those who have made this exhibition and the project possible. First of all, of course, Albert-László Barabási and the whole BarabásiLab, especially Csaba Bóth and Alice Krishenko, and the former members Kim Albrecht and Mauro Martino. Thanks also to the Ludwig Museum, to the director Julia Fabini and the curator Joseph Kiesmann for the cooperation, and to the wonderful graphic designer Sascha Fronczek. A big thank you to Anne Deuper, Christoph Hierholzer, Rainer Gabler, Philipp Ziegler, Teresa Rezza, Zachariah Feldmann, Lena Schneider and Lena Becker, and of course the whole wonderful, really wonderful team of ZKM. For this evening, I'd like to express once again my thanks to the speakers, to our audience that vividly joined us tonight, to Leonie Wagner and Sonja Willner from Baden Dolmetscher, and to my dear colleagues from ZKM Video Studio, who made it once again possible to so smoothly celebrate the digital opening. Yeah, thank you all. And
so, Clara, I only wanted to say, if I could sing like Louis Armstrong, I would say, isn't it a wonderful world that we can sit together, linked by digital technology? It's a wonderful world. Thank you so much.
Yeah, thank you all and have a wonderful evening.
Thank you. All right.